So we have now a general concept of a state in a state space, and we have a general concept of a solution. Now, and that is now what we have to do. And maybe it's a good time to stop here, or I don't know.
Okay, let's have a break. I don't know.
I could continue for 15 minutes or something like that. I don't care. I'm just I've been already listening for quite a while.
Maybe a small break. I don't know.
Small break. Okay, 5 minutes break.
For a coffee.
Yeah. 17.
Maybe an example for a semigroup would help
Yeah,
to
I
understand.
think an example would
Or just
We get it.
let them try to figure something out on their own.
I mean,
this is
I think
helping the
you
most.
give an example of a semigroup once you define what's the generator. You first define the generator, and
Oh, I
then you
can
can
already give an example of a
Yeah.
semigroup.
If there is the
infinite.
this, just the translation.
Yeah.
Yeah, but then it's interesting to see what's the PD related to this.
Yeah, but yeah, we can discuss about didactic, but I think it's good just to try something with semigroups to get an idea of what it is.
like the norm converges to zero.
Norm convergence is hard.
What this is meaning.
Yeah.
Yeah, this is actually this is
But
just-
In mathematics, you should pay attention to what when you say the norm converges to zero. It's not the same as the difference in norm converges to zero. The terminology is very important.
But this is not the difference in norm. This is difference in.
Yeah, that's the norm of the difference.
Having this is not the same as having t of tx0 in norm converging to the norm of x0.
This
The one
follows
implies
from-
the other, but not the other,
uh,
not vice versa.
Okay, maybe you can ask the question.
Yeah. For instance, you said that the value will be half,
Yeah.
but the difference in the
Yeah, this is.
L, this is
I-
difficult
I
for me to
mean-
get.
Do you know this? What this is meaning? Okay, I write it another word. I define a function and then I define it piecewise. I will define it 1 if x is 1 and 0 else. Okay, this function looks like. Yeah, okay, I need another cover. Okay? And when I calculate the norm for this function, the L2 norm, what do you have to do?
Would be the integral over a.
Here, no space.
Integral over a would be
Okay, we have 0 and 1.
0 and 1, so we have 0 and 1.
Yes.
So it is 0, isn't it? I mean,
Yeah, but there's still one point which has where the function isn't 0.
so I do 1.
But what I was thinking, aren't we assuming like a sort of continuity because if
Yeah.
the solution map has some
This,
code,
this,
1 over
So
a,
the
but
solution is of course defined for every
is it
state.
now it's the question, how do you evaluate
At a
the
certain state, you don't know what you are doing.
how would you do it at that
Okay,
point?
we
Okay, so I think of a vibrating string. The string is always at a certain position, yeah?
okay.
like we would
Just go with
So it cannot happen that is something like that.
Okay?
Yes.
We need
Finally,
to square it.
Yeah.
Okay, now we have to
explore it.
now we know almost everywhere.
No.
So
Why? But if it complies with that.
we
No,
split
with
the
the- no, it doesn't.
It's
It's
good
the
absorption analysis, not
I mean, the
Laplacian
Laplacian doesn't
like-
depend on time.
Like this level,
this
like
is what we are doing,
Or
and it's really
Okay, we
to
can try
understand.
that.
Take the
Like, you know what
Laplacian, not the
is
Laplacian,
also
but
to understand the
Laplacian.
the integral is
And
zero
yeah.
The
because
heat equation. Let me show you something.
because it has to
It's
do
more like
with
that.
the integral of a
Very
function.
original point.
Here you can
No,
see
most
that
high
it's a point that is a certain
No, the
dimension
Laplacian
of
is
the
not a
zero.
polynomial.
So whatever you measure the integral of function.
The heat equation is
set
not,
it
for
to
example,
zero.
the heat
Yeah.
equation you
But
cannot
this is tricky because
Okay.
this is tricky because you don't know how to generate
the heat equation.
The problem is
X
the function is just, if you change the function just in one point,
X of t.
this doesn't change anything for integral.
yes, it is still zero.
Yeah, that's okay, so I don't need.
Yeah,
We
This is
did
just-
it.
Yeah.
Yeah, so
So what's
this,
the point?
one
And you
point
have to
doesn't
change
change anything.
given
Yeah.
initial
So you can just ignore this one point.
Because
And
it's
so-
a set of measures zero, so you know that whenever you compute the integral in a set of
Yeah.
measures zero, is always zero, independently from the
Okay.
function.
The idea
So this
is
one
to
point
reach
which
X.
had where the function were
So what's the point?
and how
Now, what
Yeah,
do
that's what I want to know.
This-
What- How is it how?
You know, I was thinking about this, because if you have like this, you can think about approximating before like this, then you go a bit more, then you go a bit more, and at the end, what you end
The
up,
idea
that all the
was-
solution are passing through this point. So at the end, when you compute the limits, it's actually remain like this point. It's an intuition,
Yeah,
it's not,
this is
Which
this
means
is
that
just
I
the result.
define X.
You just mentioned it, you can figure out that it really is a half, but you
Psi.
actually you just
And
don't
this
care.
maps to X.
it could also,
It's also not obvious that it's for
This
every
is very
function it is a
difficult
half.
at the moment, but
It
what you
can-
do is basically.
but also if it's, also if it's there, also if it's a function,
Yeah.
The space
also if it's a
forget
function that is this,
Just look at the
this,
time variable.
this,
Consider a new
this,
map.
and the point is
It
here,
only takes time to
still
give
the
you a
same.
function.
It can also be here, there,
Basically,
everywhere in this line.
this system.
You can
now
have a point,
translates
but
into
still
something.
the,
error
when you go, not the error, but the norm, because
norm
you have
of
the
the error.
integral,
Yeah.
and so the point it can be wherever.
The error.
Still the integral of the function computed in one point is always zero. In this precise case is here, but it could be anywhere,
Is
in that line.
Laplacian, but then you just like A, and it's an operator. And this, yeah, the Laplacian is an operator. And we just call it A because it comes from somewhere. And we will see this now.
I don't know. Okay. You're waiting for me again. Oh, okay, good. There was a why don't we do an example was said and things like that. I've thought about it because I would like to definitely have my train at 5 o'clock, so I will leave here at, okay, I leave the books here. I thought you would be already completely tired of it at 3:30, but you still want to continue. Good. So I leave the books here, they will be safe here. That's no problem. Then I catch my train from here. So that means that I have half an hour left. And I want to tell you something also, but I think I will give you a homework. Yeah? And the homework is the following. And we will discuss it tomorrow morning, yeah? And I see already lively discussions among you. So you may also solve it completely and then, okay, I don't have anything to do tomorrow morning and I just continue. But basically I ask you, check C0 semigroup, property C0 semigroup. For tt is e to the power 3t 0 to the power 1t, so t, just have to look very carefully, and then I have it, because we will see this example. It's just 3 to the power 3t minus e to the power t. And this is on R2, x is R2. State space is R2. Check all the properties. So we have to do, this is a 3.
Let's check also.
Oh, I just flipped them. Oh, sorry. Good that you paid attention. I just look at a half I and of course then you see. Then this would not have the semigroup. Okay. This is the first one. The second one is the following. Now I take x is L2 0 infinity. Let's do that. And then I define tt of x evaluated at zeta is x of t plus zeta. Yeah.
We are summing the space coordinates with the time. Let's just. We are summing a time with the space coordinate.
Oh yeah, so
What was it?
velocity.
Ah, okay.
Seconds per meter. So let me do it correctly. Vt zeta. Oh, yeah, excellent. The V is on this. Per second is 1 meter per second. Yeah?
Now I'm happy.
Yeah. Now you're much more happy, of course. Yeah. No, I could even do it differently. It doesn't matter which value the V is. Let's stick to this. Yeah?
But now I have a problem with it. Because now if I evaluate x of t, the dimension isn't right anymore. Because now I have always to write x of v of t. Because I can't plug in t anymore in x. Because x depends on meter, but not on time.
Should I do that?
No, I'm just saying if I fix the problem that way, I have the problem that x can't depend on time anymore.
But x does not depend on time.
Oh, sorry, I mixed it up. Yeah, you're right. I mixed it up, I'm sorry.
Yeah?
Yeah.
This is the so-called shift semigroup. And now this is, I think, the left shift semigroup. We have to think about it. You make a picture of it, yeah? Yeah? Okay. Let's send the homework. Okay, I'm not claiming that anything is easy. Now, probably if you, the identity and the second property, if you take the time to be 0, that you then get the identity, that's most times not so hard. But all the other properties, they have to be, and some can be really hard, yeah? But just see how far you get, yeah? And maybe after this lecture you just drop dead in your bed. I don't know, that is also... Okay, so we go back. Where were we? We were here. And now I just say how to formulate, basically, the state space formulation for a partial differential equation. Because basically what I want, and I get to the Port Hamiltonian system, but that will be tomorrow, yeah? It's just first to do this, and then to tell this Port Hamiltonian. I'm still on this thing here, yeah, on this item. Let you see. This book, I just take this book because I know it quite well. The chapter on semigroups is 90 pages. Roughly. 90 pages, yeah. So you can imagine there is a lot to say, yeah? And then, that's the whole problem. You need that. But I always say, if you had for the first time state space theory, you were also spending a lot of time on what is the solution of x dot equals ax, and also writing it in that way and things like that. Yeah? Also, and then if you had an input, then oh yeah, it's just this form. Okay. But now I'm still having a partial differential equation, which I just have. Yeah? And now I start with an example. This is the transport equation, but on a finite interval. So I just have this equation. I'm looking, this is a very simple PDE, I'm looking for a function such that the time derivative is equal to the spatial derivative, and it should be in the right hand side, it should be 0, and there is an initial condition given. It's just the PDE. Okay? So there is what is it says? A partial differential equation, boundary condition, initial condition. That's just the whole terminology. And I want to write this in an abstract form. I basically want to write this as x dot equals ax. I want to write it, and I think that this must be possible somehow. This looks at it, okay, all the coefficients there are 1, that's also nice. And they don't depend on time, yeah, the coefficients don't depend on time. It's linear, I don't take products of states or anything like that. So you would think, okay, there could be a C0 semigroup with it. And solution map, which is linear in time invariant. Now we already have x of t is a function of time. As I said before the break, basically the spatial coordinate goes under the carpet. So that is just what you do. You just take x of t is just this w of t, and I forget the spatial coordinate. Or later I can plug in the spatial coordinate. Yeah, so I choose this. Yeah, and this dot is just that I can just plug the spatial. Or if you prefer it, you could also write x of t. I can evaluate it at a spatial point, and I get this. But again, with this two-dimensional surface, I see it now as a collection of lines, curves, projections. Now, and then there is a choice of state space. And I keep repeating, and there is a choice of state space, and I basically do nothing with it unless I get to the Port Hamiltonian systems. Yeah, so here, we just had L2. Let's pick L2. Yeah. We don't think about anything. Oh, that's a nice class of functions. Yeah. And that's a Hilbert space. And so, you know. Yeah. It's always good if there is more behind it, behind this choice. But at this moment, there is no more. Just want to have a simple example. We have seen L2, so I take L2. And since the spatial coordinate runs from 0 to 1, I take L2, 0, 1. Yeah. What is the time derivative of the state? Let's just, I have to differentiate this function with respect to time. But this function was in reality a function of two variables, so I have to, so the difference is the spatial, is the time derivative, and the partial derivative with respect to time. So basically, I have this side. X dot, I could see that's on the left-hand side. I just this observation. And then what is the right-hand side? Oh, let's call that A of x. Then I have succeeded in writing it as x dot equals A of x. Oh, beautiful. But what is then A? Now, what is A doing? It takes my state, and it differentiates it in the spatial direction. Which I can do, because if I have a state, I know only this curve, that you have to say. I don't know what is before and behind it, I only know this state. And A should work on that state. A cannot give me the time derivative because I know nothing in that direction. But it can give me the spatial direction. It can give me the spatial derivative. So that's what A is doing. So if you just say A of x is the spatial derivative, that is in the state space is well defined. In the state space I have only one curve basically, and there I can do it. So you see, this PDE, which was not even that complicated, I wrote it in a standard formulation. X dot equals AX. So, this PDE, and now we get, say, in the operator language, and this is really, I don't study the PDE directly, I write it as operators, and that's like you could study systems without doing state space theory. You could do it, This is also a choice I make. I study, instead of the PDE, I study operators. Or I use the operator language. It's basically to say. So this PDE has been rewritten in this. And then it's a little bit, what is A? Now we have seen what is A, but that is more like an engineering. And as an engineering, I take derivatives. Mathematician would say I'm not allowed to take derivatives because the derivative does not exist. I only take derivatives when they are existing. And then the result says something else. I have this A. Wait one moment, I have this. Where has this condition gone? Where is my boundary condition? My initial condition is not that hard. I could just write down, because I have this choice, I could just write down the x. My initial condition, my state at 0 is W0. That's very easy to translate that into the state. But where is this? It's an essential part. Boundary conditions, we will get to it later, but boundary conditions are an essential part of a partial differential equation. They tell basically how this PDE is connected to the outside world. If I have a string, it behaves completely different if I have it fixed or if I have it free. It's just boundary conditions. So boundary conditions are essential. And basically, I don't see it in the A. You see, it's just spatial derivative. No boundary conditions. So where do they go? The other problem is a mathematical problem. L2 functions are quite wild. They can have jumps, for instance. Then they are not even at their wildest. And what do I then mean by the derivative? So we have two problems, basically. To recover somehow the boundary condition, to say somehow, what do I mean? I just write this down, but wait one moment. So A is just this mapping, yeah? It's fixed in time, basically. I give it a... So A, you can just see it need not to have a state. If you just give it a function which is depending on the spatial variable, it will differentiate it. Yeah, it will do it for state functions, but it will do it for arbitrary functions. So A is just well defined. Also say outside the concept of this PDE, you would say. Huh? Just you differentiate. And then there is the nice mathematical trick. Basically what I want is that my answer lies in the state space again. I want that A maps into the state space. Now you all know if I have a function with a jump, or you all know, I don't maybe, but if I have a function with a jump and I differentiate it, I get a delta function, and delta function is not in L2. Yeah, things like that, yeah? So what is then the nice trick? You define a domain. You define a class of functions where A is allowed to work on. Yeah? You say, okay, okay, I can map outside my space by differentiation, basically, but I don't want to map outside my state space. So what I have to do, I have to restrict the functions where I'm allowed to work on. So basically, you get this. Basically, the domain of f are all f such that the derivative is in the state space again. Now that's a valid definition, but it's a very weird definition, because you are only taking you're saying I'm only allowed to take the derivative if the derivative exists, but to see if the derivative exists, you first have to take the derivative. That's a little bit weird. Now you can take the derivative in a more generalized sense, and then you can say this really, then there is a generalized derivative, and then you can ask if this function is in. But there is also another way, and that's basically what we did in the yellow book. We definitely characterized all f's with as this. And this f is then a class you could already think of continuous, but they are a little bit more. They are called absolutely continuous. And that is okay. I have to look up the definition precisely what it is. But an absolutely continuous function has a derivative, and then has a, okay, still a wild function, but basically in L1, and then you claim that you ask that that one is in L2.
This is a 1D.
This is 1D, yeah, important 1D, yeah, otherwise you get into self-left embeddings in more spatial dimensions. This become more, and then this is much easier to write down. And that is then normally done. And then you get, so this is the, basically if you have heard about it, and then I want to stop, this is somehow a Sobolev space. This is H1. The Sobolev space H1. And maybe there is a 2 somewhere, and maybe there is not, but the 1 gives definitely that I'm allowed to differentiate once, and I end up in L2. So you can see here, basically, you can also say I get this wild function. If I integrate them, then I get something which lies in the domain of A. So you already, okay, I integrate already some maybe functions with jumps, but then I always get a continuous function, but you get a little bit more. This is also not a good point to stop, because we still have the boundary condition. But there is also a hole there. Do these things have to do with each other? I could tell more about that, why that is logical, but the boundary condition is an essential part of the PDE. I cannot restrict that more and more. And so the A is the one that looks really in the spatial direction. So what we do, we put it into the domain of A. So we restrict even the class of functions further. Yeah? So here, for instance, f is identically 1 is in it. Because if I have the function identically 1, I can differentiate it. I get 0. But it does not satisfy the boundary condition. So the function identically 1 is differentiable, but it does not satisfy this boundary condition. So the boundary condition also go into the domain of A. Because basically that's information which is in the spatial direction. And say everything of the spatial direction goes into A. And A consists out of two parts. Basically the operator, what does it do? And on which functions may it work? Two different things, because I could forget this, and then A is still well defined, the differentiation. I restrict it further because I still have that condition.
These functions are only for space, the
Yeah.
time is fixed, right?
Time is, okay, time is forgotten, you could
When we
say.
start speaking about A, we
A,
just have, there is no time
we
anymore.
only look in the spatial direction,
So time is fixed,
or time is forgotten.
okay.
No, it's just the
Yeah,
point of
yeah,
view you take, yeah?
But still there is no time we have to take care of.
No,
Okay.
because the partial differential equation or the coefficients are independent of time. I can do it, yeah? You see, if I would have this PDE with a constant, the time-dependent coefficient in front of it, if I would have here, say, A of t, or say, sine of t in front of it, I could not do it. I could not forget time, yeah?
Okay.
I think it's also important to mention that when we have a PDE, we usually have, so we have partial differential equation, we have partial derivatives. You usually have time and space, and the idea is to forget the space initially and hide the space. Usually put the space, everything that's related to the space, you put it in A and its domain, and time is what acts initially in some sense. So you first look at, in some sense, some sort of a differential equation,
Yeah.
and the
I
A
agree with this. The A only works
Only
in
works on
spatial
space, yes.
direction, yeah? That's for sure.
because the A is always a differential operator in space.
Yeah. For a PDE, yeah? So, nowhere in A, basically, not in his action nor in his domain, time may pop up. And that's somehow also inherent somehow in the timing independence. That's also if you write down a matrix, you know, x dot equals ax with A a matrix, then you don't want time in that matrix. Yeah? Or if there is time in this matrix, you have to do other things, then the solution is also not equal to the power of AT.